Statics, Type 8 Hooke's Law. So Hooke's Law obviously is a whole separate question that comes up a lot of the time with simple harmonic motion and the circular motion question, which we don't cover in applied maths, but obviously I cover it in physics. But if you don't study physics, then Hooke's Law is something that's not familiar to you. So we generally will see Hooke's Law coming up when we have something that is elasticated. So in 1997 we had a question where we have a particle of weight W is attached to two light inextensible strings, meaning they are not going to be extending at all, so they're not elasticated. And we're told that it has a length of 26 centimetres. We have the other ends of the strings are attached to 2 points on the same horizontal level, which is 48 centimetres apart. And we have to find the tension in each of the strings in terms of W. Now in the second part of the question, we're told the strings are replaced by two light elastic strings. So that means that if we put any force on these strings, they are going to change in length because of Hooke's Law. So before we start the question, we're just going to revisit what is Hooke's Law. So we have this image here from a website, phys.org, and it's a nice illustration to demonstrate Hooke's Law. So basically what Hooke said was that if we apply a force to a elasticated object, such as a spring, then it will extend in length. So if we apply a force that is twice the size, it will now extend twice the distance. And if we continue to do this, eventually it would reach its elastic limit and it would no longer return to its original shape, right? So for the point in which this is obeyed, we will find that the force applied is directly proportional to the extension in the string. But there is this restoring force. This restoring force wants to pull it back to its original position. So because that restoring force is going to be in the opposite direction to the force that we are applying, then when we go from proportional to equals, we end up with this constant, and we're going to have this negative sign. So this negative sign is only because we have this restoring force trying to pull it back in the opposite direction to the force that is causing the spring to extend in the first place. So this is the formula that we tend to use, where S is the extension, or in this diagram here you can see that is X, so this extension of the spring or the elasticated object, and that's going to be measured obviously in meters. F is your restoring force, which is measured in newtons, and K is the spring constant or the elastic constant. And this can be found in our maths tables, which is on page 57. And we can see it's under forces and materials, and it's the first one on that page. So F equals minus KS. Okay, so with that in mind, let's look at this question. So we're going to go back to the question there. We're going to do part one first, where we have a particle attached to two strings, and they're attached to 2 points which are 48 centimetres apart, and we want to find the tension in each of the strings in terms of W. So let's draw a diagram. Okay, so we have 2 points, and we know that the distance between these 2 points is 48 centimetres. And we have our object is attached to 2 strings, and therefore it's going to have weight pulling on these strings. But these are inelastic, so they're not going to change in length. But of course, because the weight is pulling on the strings, we then have tension in the string, and tension always acts away from the object. There are 2 strings. We want to know what is the tension in each of these strings. Okay, so because we just have an object hanging here in suspension, then really we're not going to have any left or right forces or moments, so it's not turning. it's just hanging there. So we're really only going to be interested in the up forces and the down forces. So that means we have to basically look at the resultant of these two tensions to know what is the resultant of these two forces. And we know in physics that the resultant of these two forces must be equal and opposite to the downward force, that third force. So let's break this triangle into two. And they're going to be two equal triangles. So I'm going to take that triangle out. I'm going to call this angle here theta, and this one will be theta. So by taking that triangle out, I know that this distance here has to now be 24 centimetres. We go back to the question, the length of the string is 26 centimetres, and that's inextensible. So that means that this distance here has to be 26 centimetres. And so by completing Pythagoras there, we'll have 26 squared is equal to 24 squared, and the opposite squared. So therefore O is equal to square root of 676 minus 24 squared, which is 576, and obviously that's going to be the square root of 100, which is 10 centimetres. Okay, so if we're looking at this, then we can say, well, we can write down what is cos and what is sine. So opposite, hypotenuse, and adjacent. So I can say, therefore, that sine theta is the opposite over the hypotenuse, which is 10 over 26, which simplifies to 5 over 13. And cos theta is the adjacent over the hypotenuse, which is 24 over 26, which is 12 over 13. So we can actually see this is the 5, 12, 13 Pythagorean triple. So again, our most commonly used one, along with 3, 4, and 5. Okay, so why is that important? Why do we need that? Well, we need it because we're looking at resolving this tension into an upward force. So if I'm looking at the upward force here of the tension, that basically is going to be the opposite side in this triangle. So if it's the opposite side in the triangle, the opposite side is going to be h sine theta. So in other words, the opposite side for my tension resolved is going to be my tension times sine theta. So let me just mark that in green on my diagram. So that would give me t sine theta for this right-hand side of the triangle. So the tension in this triangle on the right is t sine theta resolved. But if I do the same for the triangle on the left, that's also going to resolve into t sine theta. So basically, because there are two strings, there are two tensions, and if I resolve the two tensions, I get an upward force there of t sine theta and t sine theta. So in other words, the total upward force of the resolved tension vectors is going to be the combined effort of the two strings. And there was the two tensions, which gives me 2t sine theta. Okay, so now I can say, well, my up forces must equal my down forces. In which case we can say that 2t sine theta must equal w. But from over here on the right-hand side, we can see that sine theta is 5 over 13. And therefore I can get tension in terms of w. So T must equal 13w over 10. So that's the tension in the inelastic strings in terms of W. So we had 5 for setting up, and 5 for our answer, and 5 for getting this 2t sine theta. So 5 essentially for our diagram being set up nicely. Okay, so the second part of the question then really is where we're looking at this Hooke's law, so something different. So we have our two light elastic strings. So the elastic implies Hooke's law. Screen is sensitive today, sorry. And again, each of natural length 26 centimetres. So we're still talking about the same length of strings, but this time they're elastic. So when we apply a force, they're going to stretch, and it'll have an elastic constant of K. And the position of equilibrium of the particle is now 8 centimetres below its previous position of equilibrium. So in other words, the previous position of equilibrium was this position here. So when we attach the weight, the strings were holding in place such that directly below that horizontal position of 48 centimetres, we saw that its position was, over here on the right hand side, 10 centimetres. So now when we attach the weight to the two strings, it bounces up and down and then comes to rest at an equilibrium position of 8 centimetres below its original position. So that means 8 centimetres plus the 10 centimetres is now going to hang at a position of 18 centimetres below that horizontal line. And what we want to do is use that information to find the value of K in terms of W. So let's draw a new diagram. Where we've got our elastic strings. Okay, so we're still going to have 48 centimetres across. But now its new position is 18 centimetres. We're going to have our tension and our tension. So again, we know the combined force there is going to be 2t sine theta as before. But of course we need to look at, there's now a new relationship here, a new right angle triangle. Because if I take that triangle out, we end up with 24 centimetres, so halfway across from the 48. It was 10 centimetres down. It's now increased by 8 centimetres, so therefore that's a downward position of 18 centimetres. So now the string length has changed, okay? So it was 26. It's now going to have increased. In other words, what is the hypotenuse here? So h squared is O squared plus A squared, we know from Pythagoras. So therefore h is going to be the square root of 24 squared plus 18 squared, which is now a new length of 30 centimetres. Okay, so this triangle here, that's 30 centimetres. So therefore the string's length is now 30 centimetres. So if it was 26, that means that it has extended. So in other words, the extension is going to be 30 minus 26 centimetres, which is 4 centimetres. So that means that the extension S is 4 centimetres, which is basically 0.04 of a metre. So now we know how much each of the strings has extended by. Well, we need to look at what is K. And if I go back to my tables, well, K is going to be found by getting F is equal to minus KS. So we also need to know what is the force. Okay, so to get the force, we're going to need this 2 sine theta is equal to W. In other words, our up force equals our down force. And therefore we have 2 sine theta must equal W. But what is sine theta this time? So let's go to our triangle. So we have, again, if that's theta, this would be our opposite, our adjacent, and our hypotenuse. So we know that it's going to be sine theta is the opposite over the hypotenuse, which is 18 over 30. In other words, 3 over 5. So if I put that in here, we're going to have 2t times sine theta. Sorry. So 2t times 3 over 5 is equal to W. And therefore the tension in each of the strings this time is going to be 5W over 6. In other words, this is the new restoring force. So then we literally just need Hooke's law. So F is equal to minus Ks. So therefore we have 5W over 6, our restoring force, must equal our minus Ks. And the minus we don't need to use for calculation purposes. The minus just signifies that it's a restoring force. So we have 0.04. And therefore K must equal 125W over 6. Okay, and because we're given our meters there, we'll put in our unit. So it would be force, which is newtons, divided by distance, which is meters. So our our elastic constant, its unit would be Newton per meter. So 125W over 6. Okay, so we had 5 for working out K and 5 for working out T. So we had 25 in total for this question. So there's another similar question to that there, which is 2011, which would be a nice one to have a look at.